I'm Ally. I'm standing in for Pamela today. I am here with Kirby Runyon, and I am trying to sort out our YouTube simulcast. So, Kirby, if you want to introduce yourself to the good people on Twitch. Okay, yay! Hi, everyone! It finally clicked in. Let me mute that so I don't have an echo. It would not be CosmoQuest if we didn't give you a little bit of sausage making. So, I do too. I live next to a Polish sausage place. It's very nice. Okay, so hi everyone. I'm going to let Kirby introduce himself and give you a little preview of what he's going to be talking about today, and then we're going to switch over to his presentation. And now they're saying that I have no audio from you. From you. You're coming in fine for me, so it is on my end. All right. God. Da, 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 da. Try this again. Just, gotta laugh. All right. Could you give me just a little test? Yeah. God, no. He being trying not to say bad words on stream. Actually, let me try something. All right, try again. Working on it. Oh my God. I'm so sorry, everyone. I am going on like an hour of trying to get this to work. Ugh. I'm a little frazzled. Okay. Let me try loop back. Okay. Yep. Okay, that should do it.
All right.
Try it
There's
now.
audio everywhere. There's audio everywhere.
Can y'all hear Kirby?
Can you test? Can you hear me? 3, 2, 1, 1, 2, 3. ABC, CBA. Alpha, Bravo, Charlie, Delta, Echo, Golf, Hotel. India, Juliet, Kilo, Lima. Mike, November.
Okay,
Oscar.
you're good.
Great.
Yay,
Okay.
I got it. I finally got it.
Way
oh
to
my
go.
God.
We got it.
So
Okay.
Let's go.
So I'm just going to introduce
yourself.
myself, right?
Yes.
Okay, great. Hello, everyone. I'm Dr. Kirby Runyon. I am a staff scientist at the Planetary Science Institute, and where I work with Ally and Dr. Pamela Gay, and I explore the solar system. And so I want to be talking to you today about some of the NASA-funded research science that I've had a chance to do in reduced gravity. And I'm going to get into the science of what allows us to experience different levels of gravity, what that corresponds to around the solar system, and then the science that enabled. So let me pause right there, Ally. Was there anything you wanted to interject? Or
No, that sounds good. I
All
am.
right,
I am here
I'm just
to
gonna dive
learn.
right in if that's okay.
Yeah, let me switch over, and there you go. Go for it. Actually, hold. I hold on. Okay. 'Cause I forgot to add the loopback audio. Okay. All right. You're good now. You're good.
Okay, I'm going to keep talking. So,
Yeah.
as we go around the solar system, we come across planets with different amounts of gravity. This is a view in orbit above Mars, looking into its hazy blue, its dusty atmosphere, looking down at a cratered surface over there on the right side. Where meteoroids and asteroids smacked into the surface of Mars, digging big holes in the ground, all happening in a gravity regime that's only 38% the gravity of Earth. And if we were to go to the surface of Mars, this is what it would look like. This is the view from the Mars rover Perseverance looking out across Jezero Crater, or actually this is from Curiosity rover looking out across the crater floor of Jezero Crater with sand dunes on the bottom there. This is all geology happening at lower gravity than the gravity here on Earth. And another planet in the same solar system with the same gravity of Mars, but even though it's a lot smaller, is the planet Mercury, the closest planet to the sun. It can superficially look a lot like the moon. It's a fair bit bigger and it has a lot more gravity, 38% the gravity of Earth. Here's a picture of the full globe of Mercury as we zoom in on a central mountain peak inside one of the craters. This is just a scene of what it might look like on the inside of Mercury. Another very Mercury-looking place, but with significantly less gravity than that, though, is the moon. This is a picture from Apollo 12 when the astronauts explored the Surveyor 3 robotic spacecraft that landed just a couple years before they did on the Apollo 12 mission. And the moon has less than half the gravity of Mars at 17%, or 1/6 the gravity of Earth. And of course, even lower gravity than the moon is orbit. If you go to Earth orbit, we can basically turn off all the gravity, and it's basically zero gravity. So it technically microgravity because due to the wonkiness of orbital mechanics, depending where you are in the spacecraft and how big it is, blah, 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 you can have like a few millionths of the gravity of Earth, but it's enough to float. And so this is astronaut Stephanie Wilson floating in the middeck of the space shuttle. But you don't have to necessarily go to space. Oh. Sorry, hopefully, is the video coming through, Ally?
Yeah, it's coming through. Yeah.
Great, so this is Mars. Let me back up. In this video, that's a Mars gravity parabola. This is more Mars gravity. Sorry about that promo code. I use that for something else. But this is what 38% the gravity of Earth looks like. This is what it is like on the surface of Mars. And then I think I'm going to do a face plant here in a second. There we go. So there's a faceplant in Mars gravity. It is a lot of fun. It's a lot of fun. You can do these butt bounces. And then, of course, even lower than Mars gravity is moon. Oh, and there's pouring water in moon gravity. This is just a little freebie, little fun thing of what it looks like. And then, of course, zero gravity. This is simulating what it would be like in orbit without any gravity around, and you're just floating, bouncing off the ceiling and the walls. It's a lot of good, clean fun. Good, clean fun. And of course you can...
Sorry, I have like I don't know if it's a weird math question or not, because I'm just like interested
Sure, what's your question, Ally?
in how they like adjust the parabola to...
Oh, I'll get into all of that.
Okay, all right. I'm just getting ahead of you. Sorry.
Yeah. Okay, so how can you turn off the gravity, or at least turn it down? On the left is a picture that inspired me as a kid. This is astronaut Lauren Shriver on the flight deck of the space shuttle, eating floating M&Ms, and this is me floating with jelly beans. Very similar kind of view. But how does this work? Well, the way we do it on Earth, without leaving the planet, actually, is in an airplane. This is an airplane called G-Force One. It's a Boeing 727 aircraft operated by the Zero Gravity Corporation. And this airplane flies in a series of climbs and dives, these parabolic arcs in the sky. It climbs up at about 45 degrees nose up, and then it steeply descends at about 45 degrees nose down. And during the time when it's transitioning from nose up to nose down, you actually can get reduced gravity. If you do it just right, you get basically zero gravity. It's like the weightlessness of space. But the pilot can adjust how broad or narrow or steep or broad that parabolic arc is in order to get different gravity levels. So if you wanted 38% the gravity of Earth for Mars or Mercury gravity, the pilot's not going to push over on the control column of the aircraft quite as sharply as he or she would for the zero gravity. And so that gives you, and then if they push over a little bit more, that gives you lunar gravity. And if you push over just enough, that gives you zero gravity. And actually, if they pushed over even sharper, that would give you negative gravity and things would go to the ceiling. But what's basically happening is, imagine your body is being shot out of a water balloon launcher like this. Or imagine you're a little Lego person inside some container, whether it's a water balloon or maybe an empty soda bottle. And imagine this water balloon flying through the air. Well, according to Newton's laws, it's going to be following a parabolic arc through the sky, described by a quadratic equation. And if your body is also following the exact same parabolic arc through the sky, there isn't going to be any force pulling you to any inside surface of the water balloon or the soda bottle, or in our case, the airplane. So you can imagine as though your body were launched out of a cannon up to 35,000 feet in the sky, just flailing through the air, and then imagine that there is an airplane magically drawn around you that's following you exactly. As your body's arcing through the sky, so is the airplane arcing through the sky, just like your body. And so there's not going to be anything making you fall down to the floor of the airplane, and you're going to experience weightlessness. Now, if that kept happening, eventually both you and the airplane would hit the ground. That would be bad. And so instead of that happening, the airplane pulls up and gently catches you as you come out of the bottom of the parabolic arc, catches you, and then pulls back up into a climb through the sky. And then you do that over and over again. And as the airplane catches you and you pull it back up, you actually experience almost twice the force of gravity in there. So we call that hypergravity. Now, I've had a long relationship with reduced gravity. I grew up in a very religious household, and as far as I can remember, the first prayer I ever prayed was, "Dear God, please turn off the gravity so I can float around." And so this is me trying on a spacesuit at the age of 3 at the Michigan Space and Science Center, sadly now closed. But I prayed that prayer at the age of 3. Nothing happened until the age of 35, when I finally got to fly in parabolic flight on board an airplane. And at this point, I've gotten to do 425 parabolas across 23 flights. I consider myself very fortunate and very honored and humbled to have gotten to do that. And I've gotten to do a lot of science. I've done this both for fun. I've done this as like a tour guide, a zero gravity tour guide, and I've also done this as a scientist. And so this is this box you see is part of my science experiment. And this thing has flown 4 times on the zero gravity airplane. And so I've gotten to do a lot of science with that. And I'm going to kind of transition now. Ally, do you want to interject at all? Or should I just keep on barreling through?
Just keep going. Let me see if we have any questions in
keep
chat.
Going. Great.
If you are watching on Twitch or YouTube, just put your questions in the chat. I am monitoring them, and I will read them to Kirby as they come.
Yeah, please, and feel free to interrupt too, because otherwise it gets more fun if we interrupt. So
yeah.
So this airplane, the parabolic flight airplane from Zero G, creates the low gravity laboratory that I need for the type of research that I do. And so I'm a planetary geologist. Let me pause on that term for a little bit. It is a goal of mine to make that phrase famous. I want everybody to know the phrase planetary geology. When I was in high school and I knew I wanted to do something space related with my life, I thought that the only space science out there was astrophysics. And so I majored in physics in college, but the truth is that I suck at math. I wouldn't be surprised if I had a math learning disability. Everything goes just confused when I try to think too hard about math. So
this is what I wish I had known And sorry, this is what
Oh,
I wish I had known in high school is that, like,
right.
it's so funny, like, now, because I majored in English because I always heard, like, oh, you can't go into the sciences because you're bad at math. And then now here I am circling around to, like, working in SciComm, and every
Yeah.
scientist I talk to is like, oh, I'm bad at math, so I just sit and do physics.
Well, you need a lot of math and physics, although you can
Yeah, yeah,
finagle
yeah.
some low math areas. Um, and so, but I found, but I would procrastinate from doing my physics homework by looking to see what these planetary missions were doing. I would go on the Planetary Society's website, see what the Mars rovers were doing. At the time, it was the Spirit and Opportunity Mars rovers. I was looking at all the little icy moons that NASA's Cassini Saturn orbiter was flying by. And I realized that the scientists on these missions, most of them weren't astronomers. A lot of them were actually geologists. And I guess that makes sense, right? Because what are the moon and planets made out of? Oh, they're made out of rocks. And if you want to study rocks, that's geology. So I guess to study the planets, you have to do geology. And so I barely finished my undergraduate degree in physics. It was like C's all the way, but I worked my tail off for those C's. And but my advisor rightly told me that he didn't think I'd be successful in a PhD program in astrophysics, and so I pivoted in my life. I pivoted from astrophysics to this new field I discovered called planetary geology. And yeah, you can have as much math in geology as you like. In fact, you can get into geophysics, and there's a lot of math there. But there's definitely a lot of areas of geology where you can get away without as much math. I would say on a regular basis, I do like high school level trigonometry and pre-calculus and algebra, and I can handle that because I've been doing so much of it. But the really advanced math is what really did me in. But so I discovered this area of planetary geology, and now I do experiments and I do geologic mapping to understand our humanity's place amongst the, if you will, the geography of the solar system. And one of my favorite planets to study, and yes, I do dare to use the word planet liberally and generously and inclusively to refer to the moon. I think the moon is a planet, and you can't convince me otherwise. So
I need to hear more about that. Maybe not today, but
maybe not today, but sure. So the moon is one of my favorite planets to study, and it's covered with impact craters. And and around all of the at least the fresh impact craters, you see deposits of junk. And this is the junk that was scraped out of the hole. If you like to go to the beach, and I know I do, sometimes you'll see where crabs have dug holes or burrows in the ground, and you see all this fresh sand outside of that hole. And that's ejecta that got ejected because the crab was digging it out of the hole. And asteroids do the same thing, except they're not on the menu at Red Lobster. And when you have a crater and it impacts the surface, it digs a hole, and then it spreads that stuff everywhere. It deposits that ejecta. And craters and ejecta are all over the solar system. On the far left and right is the moon. We've got a false color view of the asteroid Ida, that red wonky thing. We've got Pluto's moon Nix up at the top. We've got Mars's moon Deimos in the upper right with those two images there. And around all of these craters, we see deposits of ejecta. And so I've decided that I want to study a lot of ejecta. They're basically avalanches, landslides coming from the sky. Now, most craters in solar system history formed so long ago that we don't get to see craters forming very much today. So we have to go to the laboratory to study these things. And so NASA has a gun and a chamber at NASA Ames in Silicon Valley in Northern California, where we put these buckets of sand and we shoot them with projectiles going up to 6 kilometers per second. That's almost Earth velocity. And you can see a hole getting dug in the ground right here. And but I've drawn a red box here around the type of feature that I study. And this red box is around the curtain of ejecta that comes out of there. And so and this ejecta is ubiquitous across the solar system. Here's an example of ejecta around a crater on Mars as visited by the Mars rover Opportunity. On the left is a picture of the same crater viewed from above from the orbiter. And so one of the big questions I've had is how does the ejecta emplacement, that is this avalanche from the sky of rock that was dug out of a crater, how does it mobilize? How does it slide? How does it erode and deposit itself around the crater on worlds where the gravity is lower than Earth? Like this experiment here, this is all done on Earth in Earth gravity. But how does stuff like this happen if you can turn gravity down? That's really hard to do on Earth, but it's not impossible. One of the ways that we study crater ejecta is by using a catapult, this lever arm catapult. It's basically a mousetrap, essentially. And we have this steel plate. We load gravel on it. We load sand on it. We load crushed chalk on it. You could load anything on it, really. And you create a portion of an artificial ejecta curtain. And then we can put cameras along the side of it. And you have this clear-sided target box where you can see the effects of, oops, oh, that's not going to the slide I want. Shoot. Anyways, you can see here that, can you see my cursor, Ally, if I wiggle it on the screen?
Yes.
Okay, so we're looking through the side of plexiglass here, and there's plain colored gravel on the other side of this plexiglass. And on top of that plexiglass, we're depositing this colorful curtain of aquarium gravel that we got at Petco. And they are not sponsoring this talk, and sadly, but we didn't even ask them to. But this ejecta curtain, they could be if someone from Petco is watching. I use a lot of Petco supplies in my experiments, including cat litter, believe it or not. And so this aquarium gravel forms an ejecta curtain. We can see how it erodes, slides, digs into itself on the ejecta bed right there, and we're basically simulating the ejecta that comes out of this. But how does this little goofy thing we do in the laboratory translate to something multiple kilometers big on planets like the Moon and Mars and Mercury? Are we just goofing around in the lab, or do our laboratory experiments actually scale? Do they scale up to the size regimes and the speed regimes that we care about on other planets, moons, and asteroids? Well, I don't know how much time I want to spend on this slide, but there's something crazy that happens when you take something and you throw it into something else. Whether you are dropping weights off ladders into buckets of water, or you're shooting bullets into water, if you make a logarithmic plot of how much stuff you erode versus how fast it is, and you account for things like the gravity and the size of the projectile, all of your data points fall along a straight logarithmic line as long as you're plotting on a logarithmic plot. And I know this can be confusing. We don't think in logarithmic terms all the time. And I don't want to spend too much time on here except to say that it's wild and crazy, I think, that the universe works like this. These data points down here were made from a guy in the 1890s dropping lead weights off ladders into buckets of water. And they plot along the same line as people in the 1980s shooting hypervelocity projectiles into buckets of water at the NASA Ames vertical gun range in Silicon Valley. And this is for water. You get a similar curve if you shoot and deposit stuff into sand. And so these are all things going really fast. This is all stuff going kind of slow. But ejecta, even though it's the stuff that came out of an impact crater, it's also sort of a projectile in its own right. And so one of the questions we have is, does it plot along this line here in logarithmic space? And if it does, that means that it might scale. In other words, that the experiments that we do in the lab are applicable to what happens on other planetary surfaces around the solar system. And so we made a subscaled version of that catapult, literally made out of a brownie baking pan on a pivot with springs and everything. And we had CAD models, so it's real and legit. And we put it in this glove box, that is this clear-sided box that kept all the junk contained so it wouldn't float around the inside of this aircraft. And we bolted it to the floor, as you see here, and we went flying with it. Here's our forklift loading into the side of the airplane. Here's just a fun video of what it looked like. This was during the pandemic. Everyone's wearing masks, and then as the pilot pushes down, we were trying for experiments on asteroid gravity. It didn't work that great. The experiments in Mars and moon gravity worked a lot better, but it's just sort of a fun view of what it looked like. And then gravity comes back. And what that looks like is this. You can sort of see, it's kind of hard to see, but there is a catapult back here that just flung an ejecta curtain. This is actually crushed chalk. We ordered gobs of sidewalk chalk from Amazon, and we put it in plastic baggies and banged it up outside the airport hangar. And yeah, highly paid scientists. Well, not that highly paid. Don't think that we're rich, but like decently paid scientists, highly educated scientists. There will go with that. Banging up sidewalk chalk and making gravel here. And they're different colors so that you can tell the result of one experiment from the results of another, and also so that you can tell the difference between the ejecta curtain and the junk that you're, or excuse me, the regolith simulant that you're depositing it onto. And then we had GoPro cameras recording everything, taking all the data. Here's a scene of what that looked like. This is my friend Khan. This is a moon gravity parabola. Here's the catapult with the gravel on there. And we've got GoPro cameras down here. And then we're all in moon gravity. And then we're going to fire the catapult. And then this is crazy Dr. George Pantelos, who's a aerospace medicine engineer playing the djembe drums while his undergraduates do all the research work. And then I just tried a backflip right there.
It's good to be the boss.
And then not all the parabolas go according to plan. Sometimes everything just floats up and we don't get to see everything, but it looks really cool at least.
That is so awesome. I love how like all you can tell how much fun all of you are having. Like, I think that might be my favorite part. Just everyone looks right. Like just big smiles and it's great.
I wish we could take everyone along who wants to go. Not everybody is interested in reduced gravity, but for those who are, I wish we could take everybody who wants to go because it is so much fun, even while we're doing very serious science. I couldn't believe that on those days when we flew, it was literally my job to work in reduced gravity. I'm like, man, I feel blessed.
I was very sad when I was a teenager and I did space camp. It was back when they had an option that you could like pay a little bit extra to go for a ride in the Vomit Comet. And
really?
Yeah, and like literally a couple of weeks before I went to space camp, they like lost their like liability insurance on that.
Oh,
so
no.
I didn't get to go.
I'm so sorry. I hope you get another chance. Oh man.
It would be worth the motion sickness.
It is. Yes. Thank you for saying that. First of all, most people do just fine and don't get motion sick. But for those who do, it's still worth it. Like you just have to have this mindset of powering through, and just like overcoming the some of the discomfort. But okay, so remember this plot from before where crazy experiments all plot on the same line, despite these being 6 kilometers per second and these being a few meters per second. So a few meters per second is also just a few miles per hour. This is thousands of miles per hour. This is a few miles per hour, to put it in maybe more familiar terms, or kilometers per hour. And our data from the small catapult plot right here, kind of between the two lines. And so it seems like our mucking around in the lab is probably related to what's actually going on in nature. So that means that we can use our lab experiments to actually tell us what's happening in the natural world. So that's cool. That's all the slides I have for now. Let's see. But I have to jump off soon, but I'm happy to take some questions here, or talk a little bit more about this. What do you think, Ally?
Okay, yeah. Does anyone have questions? I know I'm just I'm curious, what does like lower gravity feel like? Like what does that like just what's like the physical sensation? Like how do you experience it?
It is freedom, it is fun, it is disorienting, it's exhilarating, it is counterintuitive, but the closest you can get into like normal circumstances is if you go to a pool and there's a really tall diving board and you jump off the diving board into the water. Those brief seconds or those brief moments between jumping off the diving board and hitting the water, that is weightlessness. And if you have like a soft ball to play with, you can actually play catch back and forth in your hand and see the, or just float it in front of you. So that's the closest I can describe to what it feels like. It's not like floating in water. It does not, I mean, that's fun, but it's not the same. It's not like skydiving either, because then you've got the rush of wind at you. It is like nothing if you haven't experienced it, you can't know. It's like taking a colorblind person who only sees in black and white and trying to describe the difference between green and red. How would you do that? It's based on common experience. And so until you've experienced it, you can't know what it feels like. But jumping off of objects into water is the closest you can come to it.
Awesome.
Yeah. So another thing I'll mention, and I don't have slides for this, but so yes, our impact or our ejecta experiments scale, but because we're looking through the side of this plexiglass, we're also seeing how the ejecta and the dirt on the bottom, how they interact, how they erode, how they slide, how they shear. And what we're discovering is new mechanisms that geologists need to take into account when we're analyzing rocks brought back from the moon or brought back from Mars even. Being part of ejecta is a common experience for rocks on other moons and planets or asteroids. And so if we can understand the ways that these rocks moved around, it'll help us better interpret the geologic record on these places around the solar system. Awesome. And so that's really the reason we're doing this. If we can understand these processes, that means that when we see a static picture of the surface of the moon or Mars, or we handle samples in the laboratory that have been brought back from there, we have a better sense of what these poor guys went through, what these rocks went through as being part of ejecta and cratering. So awesome. People do other lab experiments too. Like there's someone at the U.S. Geological Survey who has done lots of experiments on landslides. He creates artificial landslides on basically a giant water slide on the side of a mountain, because you never really know when or where a landslide on Earth is going to happen. And so he can instrument it to better understand the physics of landslides, which on Earth helps us protect people who might live near steep slopes. So this is called geohazard mitigation. It's hard sometimes. If you want to study volcanoes, it's dangerous to get too close to lava. And so there are people who melt rocks, make artificial lava, and do lava experiments in the lab. So by doing experiments in the lab based on how rocks work, you better understand the rock record around Earth or around the moon or other planets. So it's my hope that as astronauts hopefully bring back more rock samples from the moon, that some of our lab results will help other scientists better interpret, hey, here's a rock. Hey, here's a funny scratch on that rock. Oh, that scratch could have come from when the rock was maybe sliding along the ground as part of this ejecta deposit. And so we'll better be able to interpret what we see in the rock record.
Awesome. And I know that, I know you and Pamela have already talked about this a little bit on stream, I think. But how does all this tie into a little project you're working with us here at CosmoQuest on?
Yeah, so at CosmoQuest, we have a project called World Mappers, where people are able to map deposits of impact melt on the moon. So if people go to mappers.psi.edu, which is still a CosmoQuest project, they can actually contribute their science. So ordinary citizens, whether you're a scientist or not, and preferably not, you can actually contribute real science. We need your help mapping rocks, boulders, craters, and what look like lava flows on the moon, all using a very simple, easy-to-use web interface. And we're going to use the aggregated results from hopefully thousands of volunteers to help train AI machine learning models on to be able to do this. But right now, it takes human eyes and a human brain to be able to map this stuff. So we need you. Mappers.psi.edu. And Pamela and I have been posting and sharing quite a bit about that.
Yeah, very awesome. I'm excited because this will be like my first citizen science project since I came on board. I joined CosmoQuest. Pamela hired me like right after Bennu. So okay, sure. I like completely missed Bennu. I just saw the aftermath, the like 1,000-yard stairs. Right. But I'm very excited to participate in this one.
Oh, good. Yeah, glad to
So,
have you on board and spread the love.
yes. Well, I know you have to jump off soon, so thank you so much for joining us, and thank you for your patience while I sorted out my 5 gazillion technical errors.
Not a problem. Glad to be here. Thanks for having me, Ally.
Yeah. So, yeah, I guess that's it. Thank you, everyone, for joining us. And Pamela and I should be back, I think, on Tuesday to update you on our 911 and space adventures. So,
Ooh.
have a good one, everyone.